In the previous lessons, we learned about concentration, and concentration is represented by the letter M. Now, M is molarity, and we know that molarity is based on 2 units. And molarity basically is equal to the number of mole divided by 1 liter of solutions. In a solution, it consists of 2 things. First of all, it would have the chemical A that's being dissolved, and we call that a solute A, okay? And this solute is gonna interact with a solvent. So a solute is basically being dissolved in a solvent. An example of a solvent is water. In this lessons, we are going to look at how the concept of molarity is used in acid and base. Well, first of all, I have the Venn diagram that describes the unique characteristic of acid and bases. Well, for acids, it always produces this H plus in a solvent, specifically water solvent in most cases, okay? Now, sometimes they don't write H plus, they would have this right here, H3O plus. So basically, this H plus has reacted with water to make the H3O plus, and we have a name for this H3O plus. It is hydronium. Where we also have another name for H plus by itself. This is considered as a proton. Okay, so proton is another word for H plus. That's not talking about the proton in an atom. Another characteristic of an acid is that it has a sour taste. Think of lemon juice and vinegar. Those are examples of acids. On a pH scale, an acidic solution would have a pH less than 7. And when it reacts with metal, it would form hydrogen gas. Now here's a tricky one. When you have a solution that is made from dissolving an acid, we have to calculate pH first. Now let's go over to the bases. The bases produce an OH minus, and the name of the ions for OH minus is hydroxide. Another characteristic of a base is that it has a bitter taste. And think of soap. If you ever taste soap before, it tastes very bitter. But on a pH scale, remember acid and base are kind of opposite to each other. In this case, if acid is less than 7, pH for a base would be greater than 7 on a pH scale. And another characteristic of bases are they are very slippery. Think of soap. When you think of bases, think of soap, like hand soap. And now let's talk about calculation. When you have a solution that's made from dissolving a base, you have to calculate the O. You have to calculate the pOH first. You cannot calculate pH directly from a solution that's made from a base. Now let's look at the pH scale. Why do we care about the number 7 so much? Because this number 7 right here, it represents a neutral values. Basically, the number of acid and the number of base are equal to each other, so that 7 is right in the middle. For example, in this case, a common substance that has a pH of 7 is pure water. Let's look at this simulation, where we have pure water, just water itself. Look what happened to the pH. It is at 7. And notice how in water, we have equal to, in terms of mole, the H3O plus equal to the number of moles of OH minus. So in a sense, the pH of 7 tell you that the values of H3O plus must equal to the values of OH minus in terms of mole. And that's an example of 7. Now let's look at a solution where we have an acidic solution. Okay, are you ready? So let's look at a strong acid solution. Look what happened to the pH. It has a pH of 2. Where let's look at the weak acid solution. Of course, the pH is now higher. And let's look at the base before we move on. Look at a strong base. Look at that, pH is really, really high. But if we look at a weak base, now it's going down. So let's go back to our pH scale. This one right here, it is very basic at 14, where right here at the very low number would be very acidic, okay? So in a way, if we go down to a lower pH scale, it's becoming more acidic. If we go up this way, it's become more basic. Let's look at some example that we see in our daily life. First of all, stomach acid is right here. That's the same pH as your battery acid. And then we have lemon juice, we have vinegars, we have acid rain. Then past the neutral values of pure water, we have blood, is a little bit basic. Then we have soap right here, is at the pH of 10. Then we have bleach, which is a cleaning agent, has a pH of all the way between 12 and 13. So that is the pH scale. Now, we learned that the pH scale indicates how acidic or basic a solution. But a pH of a solution depends on two independent. They are not related to each other, okay? And these two independent factors, the first one is the degree of ionization based on its strength. Based on the strength of an acid, either strong or weak. And we just observe it, a weak acid would dissociate very little. Let's go back to our simulation right here. I have a weak acid right there. See how it's very little? This would be the acid right there. See how it has very little orange part, which is the H3O plus. Where if I turn to a strong acid, look at that. Do you see any more of this left in there? No, because it has completely dissociated. And the same thing with a strong base. Now let's look at a weak base first. This is the base right here. Notice how we still have some of the base left. We actually have a lot of the base left. But let me bring this into a strong base. Look what happened. We don't have any more of this left. It's all in colorful form. Notice how in strong base it's completely dissociated. Notice how strong base is completely dissociated in water. Now let's look at the graph, okay? So here, let's have water. Notice how in pure water we have H3O plus is equal to OH minus. So we have the pH of 7. But let's look at a weak acid. Notice how this is an acid right here. This is the same amount of water. Look at that. There are still of them. Look at that. There's a bunch of them left. And a small amount of them is dissolved into, in this case, H3O plus. But look what happened when I put a strong acid right there. All of the acid has been dissociated into H3O plus. Now let's look at the base. Notice how the weak base. There's still a bunch of weak base left. And some of them are being dissolved into the OH minus. But look what happened when I have a strong base. All the base has completely dissociated in form of OH minus. Look at the strong base. All of the base. Now let's look at strong base. It's completely dissociated in water to make that OH minus. So that's the difference between strong base and strong base or acid versus weak base or acid. Okay, a strong base or acid completely dissociated, where a weak base or acid partially, and I mean partially, a very small amount of it will dissociate in the solvent. In this case, it's water. So let's go back. As I mentioned before, strong acid and base dissociate completely. That's meaning 100% in water. And then, but a weak base or acids, partially, okay, only small amounts of percentage, very small, dissociate in water. Now let's look at the second factor, the concentration of the solution. That means how many moles are in that specific volume of solution. So how is that important? Well, we just mentioned weak and strong acid, right? And this part is extremely important. That is because even if you have a weak acid, but if you have a lot of it, it will become as corrosive or as toxic as a strong acid. That is, diluted in a very large volumes of water. So be careful, okay? And we're going to look at that mathematically. Very important. So basically, I'm saying that if you have a high concentrated weak acid solution, it can be very corrosive. But if you have a very diluted or very low concentrated of a strong acid, it will still be very harmless. And again, just a review, calculate pH from a solution that are made from dissolving an acid, and calculate pOH for a solution made from dissolving a base. And we're going to look at that example in a few minutes right now. The first task is determine if a substance is an acid or base. Remember, an acid would produce an H+, while this one would be OH-. So these are the two things that we're looking for. Let's look at this one, HCl. Does it have any OH-? No, so it cannot be a base, but it has that H+ right there. How about KOH? It doesn't have an H+, but right there, we have that OH-. And notice how OH is a polyatomic ion, so it's always stay together. And that's the reason why you have OH- next to each other. Then we have HNO3. Do we have any OH-? No, we have that H+ right there, so this must be an acid right there. And this one must be a base and an acid right there. Let's look at the next one, H2SO4. Do we see OH? Of course, now we see that H, so this must be an acid right there. How about calcium hydroxide? Right away, you see how that OH right there. This must be a base. And lastly, we have C2H4O2. This does it have any OH together? No. So right away, we have to assume this must be an acid right there. And this is the acetic acid in vinegar. And the next task is we are going to calculate either a pH or pOH from the concentration of each solution. So remember, we talked about we had to calculate the pH if a solution is made from dissolving an acid. Or we have to calculate the pOH if the solution is made from dissolving a base. So before you even do any calculation, you need to determine if this solution is made from an acid or a base. For example, in this case, we have the substance HCl. This is not a base because it doesn't have an OH-, so therefore that must be an acid, okay? So now, because it's an acid, we have to calculate for pH. But what is pH? And what is pOH? Well, notice there's a reason why it has P in front of both of them. That's because this letter P right here, it actually represents negative log of something. So P is equal to negative log with a base of 10 to something. And on your Google calculator, I'm referring to this log right there. So if you want to type in negative log, would be negative and log. And that's pretty much it. So let's do an example problem together. In this case, I have this acidic solution made from that concentration. So all I have to do is take negative log of 0.005. So let's plug this into our Google calculator. We have negative log, okay, 0.005. And there you go. The pH is equal to 2.3. Isn't that easy? Let's try another one. Here we have 0.5. Here we have 0.005 molarity of NaOH. So this OH tells you that this must be a base. So we have to calculate what? If it's OH, we have to calculate pOH. So in this case, we have negative log of 0.005. Let's plug this into a calculator. We have negative log 0.005. And there you go. We have pOH equal to 2.3. Now, pOH of 2.3 is not the same thing as pH of 2.3, okay? They are completely different, and we talk more about that later. Now, let's try a more complicated problem. Here we have the same thing, right? In this case, this one is not a base because it doesn't have an OH somewhere, so this must be an acid right here. And let's plug this into our calculator. How would I plug it into our calculator with scientific notation? So the same thing, let's erase this. I have negative log of 3.5, and what do we use to represent time 10 to the power something? The exponent power, and it's negative 5, And there you go. We have our answer 4.46. So in this case, a pH is equal to negative log of 3.5 e to the negative 5, which is equal to, what is it again? 4.46. There you go. And of course, in this case, we have the same values at that one, but this is a base, so this must be what? Right there, that tells you this must be pOH. And because it's the same values, we have negative log of 3.5 e to the negative 5, give us a pOH of 4.46 as well. And they are not the same thing, okay? So keep that in mind. And lastly, we have 0.1 molarity of acetic acid. Let's plug it into a calculator. Pretty easy. So we have negative log. Let's erase this. So let's plug this into a calculator. Negative log of 0.1. And what do we have? Oh, there you go. We have pH of 1. And how do I know it's pH? Because this is an acid right there. Okay, it doesn't have the OH. Let's try another one where this one's a little bit tricky. Here I know HCl is an acid, but the concentration is extremely concentrated, and we're going to work with this concentration later in our class when we do a lab with hydrochloric acid. So now let's plug into a calculator to see what happens when we have a solution that is highly concentrated. Negative log of 3. Look what happened. We have a negative pH. So when we have a negative pH, that tells you that we have more of the acid than the solution. In this case, we have a negative pH. That tells you it is extremely corrosive. So don't touch it because you're going to hurt yourself. When we have a pH of a highly concentrated, which is more than 1 molarity, it will result a negative pH. And that's pretty much it about acid and base.